Okay, Astronomy 1020 Day in the house. Give it up. Woo! Now, last week we did a special homework, and the special homework was, according to this class, homework number 8. But in order for me to not have to resequence the homework numbers, we're actually going to call this homework 8 again, okay? And last week's was 8, but we're going to rename it 7.5, okay? I think we have to do that. Now, we have a slightly different assignment. I had to change the numbers because I borrowed a few from Chapter 16. We're going to do 52, 53, 54, 55, 56, all in a row. They're all good and interesting problems, but a couple of them are hard and long, so I want to try to get right through this. I'm going to do the reading so that the students at home can pick it up. And in fact, I think the best way to do this is to flip it and reverse it so that they can see the text as I'm reading it. Let's hit that autofocus key. Okay. 52 is titled Water and Molecular Clouds. The water molecules in your body were once a part of a giant molecular cloud. Only 1/1,000,000th of the mass of the molecular cloud is in the form of water molecules. The density of such a cloud is 10 to the negative 21 grams per cubic centimeter. Estimate the volume of a molecular cloud that has the same amount of water that's in your body, and how does this volume compare with the volume of Earth? That's a lot of data. We got to get it up on the board. Let me recenter this on the chalkboard. Okay, so let's start by taking down our givens. This is Chapter 16, number 52, Water in a molecular cloud. Today, I showed you guys some cool images of the Eagle Nebula, these giant pillars of creation. Those are examples of giant molecular clouds. They're full of dust and gas. Okay, let's see if we can write down the givens in an intelligent way. They say 1/1,000,000th of the mass of the molecular cloud is in the form of water molecules. So that means the mass, let's use some non-threatening colors for our students here. The mass of the H2O, let's see, how do I put a millionth into scientific notation, students? What would a millionth be in scientific notation? Very slick. So the mass of the cloud times 10 to the minus 6, or 1/1,000,000th. That's how a pro would talk, Caleb. I like your moves. We got some good folks here. Okay. Now, they also tell us that the density of a cloud, so the density of the cloud is 10 to the minus 21 grams per cubic centimeter. They want to estimate the volume of a cloud that has the same mass as the water in your body. So let's go ahead and draw a little picture, because here's my giant molecular cloud, which we know is mostly full of hydrogen, here represented by the little black pellets. Scattered throughout this cloud at a ratio of 1 part in a million would be some water molecules. Let's represent the water molecules as some little boomerang molecules. And they're going to be randomly scattered throughout the cloud in random places. Okay? Now, meanwhile, we have a dude. Here's a nice picture of a dude. A dude is mostly made of water, right? What fraction of your body do you think is water? I think it's 60, 70%, right? I like 70%. Let's do that, okay? Some people say a man's made out of mud. But a poor man's made out of water, okay? So, the mass of a human times 70% will be the mass of water in your body. So, I don't know, what we use as a typical mass of a human. Remember, your mass in kilograms is approximately half your weight. So a 200-pound person would be 100 kilograms, right? So 200 works for me. So 100 kilograms of man times 70% gives you 70 kilograms as the mass of the water in a human. Does that sound good? Now, do you guys understand the gist of this thing? If a giant molecular cloud contains water, that water is spread over a huge volume of space. It's not like Jesus made the water in your body. It's not like the water was carved out by Earth. All that water used to be in outer space, and now it collected itself on our planet. And that water is all spread out through these giant molecular clouds in space. How much space gas would you have to suck up to get enough molecules of water to squeeze a human out of life? Or into life. Into life, not out of life, sorry. All right, what do we do? What's the best way to go about this? I can, of course, tell you what to do, but that wouldn't be any fun. Wouldn't it be funny to see you try to figure it out? Paige.
I think it's really wrong, but finding out the mass of the water in the molecular cloud and the percentage.
So if you think about it, that's a great idea. You're not totally wrong. The mass of water that we're looking for in the cloud should actually be the same as the human, right? Because we only want, how big a cloud do I need to make one human? So yes, Paige has just connected that the water mass of the human is the water mass we need in the cloud. But that's not the same as the mass of the cloud. That should be much bigger. How many times bigger? So don't say weaselly big shit like that. That's for weed smokers and astrology worshippers and all the ding-dong, energy crystal, tinfoil hat people have to deal with all fucking time. This is a place free of those doinks, okay? We are going to do this right. So we know the mass of the human, the mass of water we need is 70 kilograms. What does that imply about the mass of the cloud? A million times greater, right? See, if the mass of the water is a millionth of the mass of the cloud is a million times more than the mass of the water. So what is the mass of the cloud then? No calculators required unless you're really, really stupid. Like, can anyone multiply that times that? 70 million, okay. 70 million kilograms. Now we know how much hydrogen cloud we need. But they don't want the mass of the cloud, they want the volume of the cloud. Let's picture a spherical cloud. Imagine that the cloud has a radius, r. We know some things, right? If it's a spherical cloud, we should know what its volume is. What's the volume of the cloud? Pi r squared is the area of a disk. That'll come out. 4/3 pi r cubed. This is a famous equation that's good to know. Volume of a sphere is 4/3 pi r cubed. What the hell does that got to do with anything? How am I going to figure this out? I know the mass, I don't know the radius. What should I do? If only I had some other given that would help me turn mass into a volume. Sorry? Density. Oh, right. Density is mass over volume, right? So by algebra rules, or by algebra law, volume should be mass divided by density. All right. Let's shift over to our next board here. We'll leave that up for a second. Excuse me. Choking here. All right. So let's see what I got. I know that the volume of a cloud is mass divided by density. I know the mass is 70 million kilograms. And I know the density is 10 to the minus, I don't like these units. Something's bothering me here. What's my beef? What do we do about that? let's convert kilograms to grams. What's the conversion factor? Can you do this in your head? You should. How do you do that in your head? 70 times 10 to the 9 on top, but then if you divide it by negative 21, it becomes... Dividing by 10 to the minus 21 means adding 21 zeros, right? So what's my final answer? Huh? Yeah. 10 to the 30 has a name. What is that? I think 30 is 2. Oh, what are my units though? No. That's Brian. So they say, let's compare this to the volume of Earth. The radius of Earth is 6,400 kilometers. And if I use the conversion factor 100,000 centimeters per kilometer, I can quickly find out what the volume of Earth would be. 4/3 times pi times 6,400 times 10 to the 5 centimeters cubed. What does that give me? Are you confused about what I did there, Malcolm?
105 or 10 to the 5th?
That's 10 to the 5th. Okay. It's 100,000 centimeters. There's 1,000 meters per kilometer and 100 centimeters per meter. So that gives you 100,000. 10 to the 5. Let's have a B-roll of our students hard at work doing their calculations. Look at these guys. Look how hard they're, most of them, but not all of them are working.
Targeted comment. Legal to not deny it, therefore you know it's true.
Caught on camera, what can I say?
I support that.
Anyone got a number? A number I can trust? I better get a calculator because Julie, could you please take out a calculator and pretend to push the buttons? Make sure this one's a better than card.
141 times 10 to the 27.
Units?
Yes,
Huh?
70 squared. I mean,
Cube. Okay, so that means I have 7 times 10 to the 31 over 1 times 10 to the 27 is 7 times, what's 31 minus 27? 4. Or 70,000 times more volume than Earth. The water molecules that make up your squishy little body, yeah,
I did 31.
because I went from 70 times 10 to the 30 to 7 times 10 to the 31, right? Your water in your body was spread out a volume of space 70,000 times greater than the volume of Earth. I don't think that's quite a moon orbit, but it could be. If I were to figure out the radius of such a cloud, I would invert the volume to do, let's see, 4/3 pi r cubed. So 3 times the volume over 4 pi cubed root. And if I plug in 70 times 10 to the 30, 3 times 70 exp 30 divided by 4 divided by pi. 3 times dx divided by 4 divided by pi. Then I take the cube root. I get 25 million centimeters divided by 1 dx 5. I get 250,000 kilometers. You know what that is? That's half the distance to the moon. So that's half the moon's radius, the moon's orbit. The volume of water in your body was spread out over a sphere whose radius was half the orbital radius of the moon. Okay, that takes care of 52.
We don't have much water.
Or rather, the water is distributed so thinly over space, is the real meaning, right? If you find it interesting, feel free to write that interesting statistic. All right, moving on to 53. Not gonna lie, 53 is a bit of a whopper.
This wasn't.
No, we did not. We might cloud it up. Okay, get ready for a four-parter here. Interstellar dust grains. Having trouble with my autofocus. There we go. Dark interstellar gas clouds contained. Are we ready, guys? Dark interstellar gas clouds contain so many dust grains that starlight cannot pass through, even though the dust grains are tiny and the spaces between them are quite large by earthly standards. Typical dust grains have a radius of 10 to the minus 7 meters and a mass of 10 to the minus 14 grams. Estimate how many dust particles there are in a cloud containing 1,000 solar masses of dusty gas if 1% of the cloud's mass is in the form of dust grains. All right, let me help you get down these givens and make some wild kind of sense out of all this. I'm going to try to go quickly here. As soon as I can find my marker. All right. So, this is chapter 16, number 53. Sorry, this is a good marker. Dust grains. Okay, so here's a little dust grain, and let's give it a little radius, little r, and a little mass, lowercase f. What they've told us about dust grains is that the radius of the grain is 10 to the negative 7 meters. Pretty tiny. Let's see, 10 to the negative 14 grams is the mass. In part A, what they're looking for is number of grains in the cloud. And they, oh, Caleb's correct. The unit of mass is grams, but I was having a weirdo moment there. Okay. I have a weirdo moment every day. Okay. So,
I was going to say it happens a lot.
I know. The mass of our cloud in this case is 1,000 times that of the sun. And we know from our lectures today that 1% is in the form of dust. Here's my idea. To find the number of grains, n, of the cloud, I want to divide the mass of the cloud by the mass of the grain. Does that make sense to you guys? If the cloud is 10 kilograms, and each of the grains is 1 kilogram, you'd have 10. But of course, those numbers aren't correct at all. The mass of the, oh, sorry. No. Not the mass of the cloud. I goofed up, right? It's not the mass of the cloud, but the mass of the total mass of the dust in the cloud. Yeah? Because the number of grains should equal the total mass of dust. So the mass of dust is actually 1% of the mass of the cloud. And the mass of the cloud is 1,000 solar masses. So 0.01 times 1,000 times the mass of the sun divided by the mass of a little grain.
Let's say M9 then. What does that say?
Where?
At the bottom.
That's grain.
Oh. Sorry.
So, I happen to know the mass of the sun is 2 times 10 to the 30 kilograms, or multiplying by 1,000, 2 times 10 to the 33 grams. Let's see what I get for the number then. The number is 0.01 times 1,000 times 2 times 10 to the 33 grams divided by 10 to the negative 7 meters. I bet at least someone up there in our studio audience could do that in their head. What do you get if you do 0.01 times 1,000? 10. 10 times 2 times 10 to the 33 plus 7. And what are my units?
Grains.
Oh, sorry. I did the same stupid thing I did earlier.
Grams, right?
No, grams cancel out, and it's
Grain.
grains. It's unitless, right? It's just doodads or dillybobs or something. But if we want to say something, we can call them grains. But it's actually unitless, right?
It actually likes to come up with it.
Yeah, we call them 2 times 10 to the 41 dillybobs. That is the answer to part A. Box it. Okay. Yeah. Okay. Part B says, estimate the total surface area the grains would cover if you put them side by side. Assume the grains are spherical, so they each have an area of a disk, pi r squared, where r is the radius. Put your answer in square light years. Okay, so let's check this one out. In part B, we're going to imagine that we make some chainmail out of dust grains, like we're headed over to King Richard's Fair, okay? But for even bigger nerds. All right, so here's all my dust grains, and I know that each dust grain has a little area. The area of a little dust grain is the area of a little disk, pi r squared, okay? The area of all of the grains side by side, tiny target disks. So, we know the number of grains is 2 times 10 to the 41 multiplied by pi multiplied by 10 to the negative 7 meters. Was it meters they give that to us? Yeah. Squared. Now, I'd say 2 times pi is about 6, right? Or maybe 6.2? Is it 6? Yeah. 0.14 is 15. It's 15. It's like 6. Yeah. Better for Josh. Good. It's like 6.3 times 10 to the 41. Negative 7 squared is negative 14, right? 7 times 2 is 14. So 41 minus 14, can anyone help me with this? That's 31. 7? Yeah. 6.3 times 10 to the 27 meters. Feel free to, meters squared, right? We want to just fact check that real quick to make sure we didn't botch.
Is that 10 to the 27? Yeah.
Yeah. So 2 exp 41 times 5 times. Yep. So the conversion from meters to light years. 1 light year is 9.5. What did we call 10 to the 15 down? It was a funny name for that unit. It was petameters, right? Remember petameters? All right. But we have to square. To get square conversion factors, square light years to square meters, we have to square. So we do 6.3 exp27 divided by 9.5 exp15 squared. I got, wait, this doesn't make any sense. This is wrong. Something is wrong. Don't tell me this is the second time today this is going to happen.
Okay, this is the second time today. Do you ever read the benefits? It's illegal.
I know what the answer should be, and I'm a little off, so I just got to think about what I'm doing wrong here. I feel good about part A, right?
What's the answer supposed to be?
I think it's supposed to be around 700 square light years, and that's not what I'm getting. I'm off by a factor of 100,000. Somewhere a kilometer was not properly turned into a centimeter. All right, hold on. Let me just, can I pause this? Okay, after 1 minute of silent meditation, I've discovered my error, and my error is in part A. None of you even know what the fuck I'm doing, or you would have caught the error. That is my error. Why?
Because it's a negative exponent.
originally I wrote this down.
How's that sound?
I'm not racing.
Look at your givens.
It is
The number of grains is the mass of the dust divided by the mass of a grain. I put in the radius of a grain.
Oh, so it should be 14.
Negative 14. I thought I did the same thing that I did with Caleb, where I accented the wrong units. That's what made this especially tricky to figure out. It's 10 to the minus 14 grams. All right, let's try this again. 0.01 times 1,000 is 10. This is 2 times 10 to the 34, and now add 14 to that. Malcolm, why you peed?
just called in.
Oh, okay.
Next time I walk around the school.
Yep. Well, they can just take that airplane mode. 34 plus 14. 48? Wow. Someone's dumb. I think it's me.
Don't comment.
48. It's not me. It's you. Okay. Here we go. 10 to the 48. Right?
I like to think it was still.
34, 44, 48. Times 100. All right. Now, moving back over to where we were in part B before I screwed up, that changes this to 48. And what does that change this to? It'll still be 6.3, but now it'll be times.
Negative 14.
Oh, thank you.
Yeah.
No, this is the radius.
Okay.
That part was right. So 48 minus 14. 38, 34. Did I do that right?
Yeah, it's the right one.
Now divided by 9.5 exp15 squared. You gotta go? Oh,
No, I was just using the bathroom.
oh, okay, sure. 6.3 exp34 divided by 9.5 exp15 squared. There we go. 700 light years squared, just like I expected. That's the total area of all the grains. For the record, that pause only lasted 1 minute. It only took me 1 minute to figure it out.
It was 30 minutes.
No. All these kids
We've
are
been
getting.
here for days. So much.
Someone's getting a minus 10 on their exam. Okay.
I don't know what we got.
They have ways
I'm
of-
just trying to.
We
tell
have
the
ways of correcting bad discipline here. Okay, let's try part C. Part C says, estimate the total area that the cloud covers, assuming that its density is typical for a molecular cloud, 10 to the negative 10 to the negative 21 grams per cubic centimeter. So they're telling us typically molecular clouds, like in the previous problem, have a density of 10 to the minus 21 grams per cubic centimeter. What they want to know is, if this is the cloud, what is the area of the cloud as a photon passes through it, right? Cut the cloud in half, and it's a big-ass disk with the same radius as the cloud. This is going to get fun. So the area that the cloud will have is a big disk whose radius is that of the cloud. We know that the mass of the cloud is 1,000 times the mass of the sun. 1,000 times the mass of the sun in grams, 2 times 10 to the 33 grams, gives us 34, 35, 36. That's 2 times 10 to the 36 grams. We can now calculate the volume of a cloud from its density. Sliding this over, the volume of a cloud is its mass over its density, 2 times 10 to the 36 grams over 10 to the minus 21 grams per cubic centimeter. Guys, what's 36 plus 21? 57, right?
That's so
That's 2 times 10 to the 57 cubic centimeters, because grams cancel out. The radius that such a cloud will have is the inversion of the volume formula. It's the cubed root of, 4 times volume, 4/3 pi. Sorry. It's 3 times the volume over 4 pi, just like it was in the last problem. So, this we're going to need a calculator for. Cube root of 3 times 2 times 10 to the 57 cubic centimeters over 4 pi. I'm going to show the studio audience how to punch this into their calculator. Where's the, okay, here we go. So, 3 times 2 exp57 divided by 4 divided by pi equals shift cube root. What do y'all get? Same thing that I get?
Yes.
What?
I don't know.
Yeah, because you didn't do it, you lazy bastard.
I just finished writing.
Yeah, no, you're just going very.
Apparently you guys want this to take an hour and a half. You thought you wanted
I'm
to...
trying to write this down.
I'm dyslexic, okay.
Don't make your disability a crutch, make it a virtue, okay? 7.8 times 10 to the 8, 10 to the, what'd you get, Caleb?
10 to 8.
Yeah. Now, here's the thing, Caleb. What are the units here?
Centimeters?
We should really convert this to light years now. Caleb, we're going to need at least a 2-part thing here. Why don't you show these guys how it's done? Set up my units for me, Caleb.
Multiplied by the, okay, centimeters on the bottom, meters on the top,
Uh-huh.
and then meters on the bottom.
Good. I don't know if you guys know those conversion factors, do you? I've only said them about, 10 petamillion times. Let's remember here. 1 meter is how many? 100 centimeters, right? So 1 meter is 100 centimeters. 1 light year is a petameter. 9.5 petameters, I guess. So let's punch that up. Punching, we have 7.8 exp18 divided by 100 divided by 9.5 exp15. This cloud has a radius of 8.2 light years. Now, the area of the disk of the cloud is pi r squared. So do pi times 8.2 light years squared. Pi times 8.2 square key equals.
Is that pi?
Yep.
Just like the.
I get 200 square light years. Hey class,
Yes.
we got a wee bit of a conundrum here.
Oh no.
The area of all of the grains, the area of the grains is 700 square light years. But the area of the cloud is only 200 square light years.
Oh no.
How can the area of the grains be greater than the area of the cloud if the grains are inside the cloud?
Wait, is the area of the cloud like this area or? is
It's
it
the
like-
cross-sectional circular area. That's
Okay,
important. So what?
Then the cloud is like a 3D shape and you're just taking a small 2D slice of it. So there's-
Not a small TD slice. The problem is the grains are distributed forwards and back. We imagined a circular slice through the cloud. But if you stack all the grains up forward and back, they actually have more collective surface area. But what if you're the photon? The photon sees the collective wall of grains as a big chainmail wall. So in part D, the final part of this problem, they ask, what is the probability that a photon passing through the cloud will hit one of the grains? So for part D, the probability to hit a grain is the area of the grains divided by the area of the disk of the cloud. It's 700 square light years over 200 square light years, which is about 3.5. What does that mean in percentage space?
In percentage?
Yeah.
Isn't that like over 300% or something?
That's 350%. What does it mean if the photon has a 350% chance to hit the grain?
It's almost hitting the grain.
It's not going to always hit a grain. A photon will hit 3 to 4 grains on their way through the cloud. Hey, fine, that's why I make the video, but you always stop. You've got to do that. And then you can fast. Or you're going to get in trouble. Okay. That means a photon will not just hit one grain, but it will hit on average 3 to 4 grains on its journey through a cloud. And this is how we get reflection nebulae. The beautiful nebulae that scatter blue light are based on this principle. This is the concept behind a reflection nebula. In fact, this is really explaining the process of extinction, but I hope so. Took a little bit longer than I wanted today. Yeah. I see your point.
Even if this video isn't posted though, I think most of these individual problems you've done in other videos, so I should be able to find.
Not sure about that today,
Really?
because I swapped a few out, but maybe. Anyways, I'll try to post this video.
Great.
I am sorry about that. I didn't realize how long we were going over. Huh? Yeah, okay.
That was the best bet.
Huh?
I was just saying that was the best bet, because you're gonna lose
Yeah,
class at some point.
yeah. We'll cut out the last problem, which is the hardest, one of the hardest ones. Okay. Yeah. I think that's a good idea because I'm going over time budget here. I'm going to nick off 56. I think that's a great idea. The last two problems are really, really quick and easy. Okay? Quick, like 5 minutes tops, maybe for each. Under 5
I can stay for that much longer.
Under 5 if you pay attention. Oh, like if you focus.
Okay, mine is gone, so I can focus.
Okay, that helps. All right.
We could just start saying next to each other or something.
Mine's helpful, you can't do that.
If there are
You know,
multiple
it's crazy
sections to these,
willpower,
or
Yeah.
it's a crazy thing.
Huh?
are there multiple sections to these?
No.
No.
both 53
Like the sound that came out
and
when you
50. See, this is the kind of stuff that's going to slow us down. If you guys cannot simultaneously goof off and bitch to me about time, that's an unfair problem for me to solve. I'm trying my best. So chapter 16 is 53 is going to involve a legendary formula called the Jeans mass. Sorry. 54 involves a problem, and 55 involve a problem about the Jeans mass. That is the condition to form a star. And they place it in terms of an equality. The minimum mass that you need to form a star is 18 times the mass of the sun multiplied by the square root of the temperature cubed divided by the number density. It's actually not a very complex formula. It does depend on us inputting the temperature in Kelvin and the number density in particles per centimeter cubed. But it only takes a minute to solve. These problems are just a basic plug and chug kind of deal. Okay. First problem. An isolated star-forming cloud. An isolated molecular cloud can have a temperature as low as 10 Kelvin and a particle density of 100,000 particles per cubic centimeter. What minimum mass does such a cloud need to form a star? This is a straight up, not complicated plug and chug, okay? So we've got a cloud with a temperature of 10 Kelvin and a number density of 100,000 particles per cubic centimeter. Notice that we write particles per cubic centimeter as 1 over centimeters cubed. The minimum mass we would need to form the cloud would be 18 times the mass of the sun multiplied by the square root of the 10 Kelvin cubed divided by, notice the way I'm about to write particles per cubic centimeter. Centimeters to the -3. It's a little bit of a trick. Okay, let's try to punch this in together. It's not super hard, but it might cause a little confusion. Now, I'm showing the people in the video, but I'm going to try to talk you guys through it. I hope that works. Let me know. Why don't we start with the inside of the square root? Type 10, hit Shift, and then hit your X cubed key, which is the backspace key. That's next to the plus minus. Now divide it by 100,000. You should have 0.01. You already got lost?
Yeah.
All right.
Wait, 0.1?
Yeah, 0.01. All right, you guys can't handle that. You're going to have to, I'm going to put this up on the board, okay?
I got 0.1.
0.1 is, I got 0.01. All right. Watch, can you see my calculator? 10.
No, we can't hear you.
Wait, it's glitching.
There we
There we
go.
go.
Hold on. All right, type 10. Now we're going to hit Shift Cube. Divide by 100. And for 1,000, we'll do 1, 2, 3. Equals. Now we're going to square root it. Shift square root. Now we're going to back multiply times 18 to get 1.8. That's our answer. 1.8 solar mass units. Do you guys know what the spectral type of that would be? These are the kinds of questions I'll ask on the test. The spectral type of the sun is what? So this should be the letter directly to the left of it. OBA, fine grow. Yes. Nicely done. All right, let's do the next problem. It's just as easy. Can I erase, or do you guys need to say? Julian?
I'm good.
All right, 55. This is the same exact problem, just with some different conditions, okay? So in 55, it says masses of the first stars. Let's see if I can get this in here. I can't focus when it's flipped up like that. I'll just read it. Models of the first star-forming clouds indicate they had a temperature of roughly 200 Kelvin, so this is masses of the first stars. So early in the history of the galaxy, the clouds would have the following conditions. They'd have temperatures of 200 Kelvin, wow, that's hot. And number densities of 300,000 particles per cubic centimeter. They want us to do two things. Find the mass of the star that would form. And they also want us to estimate its age. Okay, we're going to plug this into the Jeans mass formula. The mass of the cloud has to be at least 18 times the mass of the sun times the square root of T cubed over the number density. Plugging in a temperature of 200 Kelvin, sorry, not squaring it, but cubing it, dividing it by 300,000. Can you guys remember what to do here? (200 to the power of 3 divided by 300,000). Oops. 300,000 square root times 18. What did you guys get? Very good. 93 what? Solar mass units. What type of star would that be, the spectral type? A wicked super O. Remember that O stars up here, the highest mass they even showed you there is like 60 solar masses. So look here, the estimated age for one of these is 10 to the power of 7. That's 10 million years. This thing would only last for less. So the age of this thing would be less than 10 million years. These are the legendary population 3 stars, which astronomers have hunted for years and never found. This is supposed to be the first wave of star formation that would have no metals and only be made of hydrogen and helium from the Big Bang. Okay, we went a wee bit over, but at least we got some work done. We're going to call it there. I'll try to post this video for those who had to leave early. People watching from home, you get the same deal the in-person kids get. 4 problems. See you later, bye.